So just like we have this average heat capacity for an individual species, we also have an average heat capacity for the reaction itself, for this delta Cp, which we have. So that is again, the purpose is to sort of hide the integral term. And so then you can rewrite that equation up there. So I wanted to touch on this again because it was towards the end of the class. I definitely don't want you guys to confuse this term, this one, and this one. Okay? So if you see the delta, think reaction. Same way that you have a heat of reaction, right? A heat of reaction is exothermic if it releases energy. It's endothermic if it consumes energy. Here this delta is saying, how does the heat capacity change as I do the reaction? Does the heat capacity increase? Does it decrease? That's what this is talking about. And then the hat just means this sort of averaging. And of course, the subscript I is for a specific species. Okay? So you're not always going to be given one of those average heat capacity values. So do we have a relationship that relates the heat capacity of a material to the temperature? Yes. So this is an empirical formula, kind of like the one that you had on the test for the equilibrium constant, where you just have a bunch of constants times temperature to different factors. Sometimes these will be simpler like this, where you just have a first and a second order. Sometimes you'll have things like log, inverse order, fourth order. Depends on how detailed they want to give you that parameter, in this case a heat capacity. And so these constants are just listed in the table. And there's a lot of sources for these sorts of data, including online. You can find things. I'm trying to remember the company. Novel, is that it? So they've got these tables. You can find them in Perry's. So let's look at an example, not of dealing with heat transfer in a reactor yet. We're going to do that a little bit later. But let's just look at a simpler one to start with. We're going to calculate the heat of reaction. All right, so the reaction of interest is nitrogen plus hydrogen goes to ammonia. That's ammonia synthesis, and we want to find delta H at 150 Celsius. Okay, so the formula that we use, delta H of reaction at some temperature is equal to the delta H of reaction at standard state plus the integral from whatever that reference temperature is to the temperature we care about, delta Cp dt. Not the heat capacities of individual species, but the delta one. So all of those species have been multiplied by their stoichiometric coefficient. Okay, so what's the stoichiometric coefficient for nitrogen? -1. And hydrogen?
-3.
And then +2 times the heat of formation of ammonia. What's the heat of formation of nitrogen? 0. So elemental diatomics, right, always 0. Same with hydrogen. And this value, don't expect you to know off the top of your head. -11,020 calories per mole. So why do I put per mole of nitrogen up there? Yeah, because that's my basis, right? You can define when you're calculating these. And that's because its stoichiometric constant is just 1. So whatever value we get is going to be per mole of nitrogen, because that's how we wrote out the reaction. That's how we defined our stoichiometric coefficients. Actually, that's how we did it in the notes, but I kind of hate that. I think this is a little bit clearer, because now if you look at what we have, you have delta H of reaction. These both go away, right? And you have 2 moles of NH3 per mole of nitrogen. So where did I get that? From the reaction. And then over here you get -11,020 calories per mole NH3. So the product does have the units that he had in the notes. But again, I didn't really like how he has it. Is that clear? Clearer, hopefully. All right, but that's at standard condition. All right, that's just this part. We've still got to deal with the rest of this. Okay, so you're given Cp for hydrogen with a hat 6.992 calories per mole hydrogen Kelvin. And you're also given the same for nitrogen. So what do we do now? Do we just add them? That's it? Yeah, we have to leave in the stoichiometric coefficients. So the average with now the delta is, as you guessed, stoichiometry coefficient for each species and the average for each species. So you get 2 moles of ammonia per mole of nitrogen times, for ammonia we've got 8.92 calories per mole of ammonia Kelvin. So the moles of ammonia cancel. Question? And then the same thing here, you get subtract 3 times, what's the hydrogen value, is 6.992 minus 6.984. And so because you're using those stoichiometric coefficients, now even though they had different units, now they all have the same units, and you get a value of negative 10.12